Morning, everyone. We'll just wait for another couple of minutes for more people to join, starting at 11:05. No quizzes today. We didn't have any new pre-session reading material, so all the quizzes for Spark, or I mean, the quiz for Spark was last week. No quiz today. Okay. All right, let's begin. Let me, by the way, post the Slido link again on the chat. Okay, there you go. So as I said, no test for today, no quiz. We just want to get through the rest of what remains to be seen for Spark. Someone on Slido asks to start with a very quick recap of NRDD. There is a more detailed slide coming later on exactly what an RDD is. What I'll say for now is that, well, an RDD is, I mean, the term means, or actually, I won't cover that now. Sorry. In I think like 3 or 4 slides, we go over exactly what is recorded for an RDD. The important thing is that RDDs don't hold any data, right? So the RDD itself only records the lineage of data. So how to produce what data the RDD is supposed to hold. The RDD itself holds no data. Okay. So I think this is where we stopped last week. Let me see. Yeah, this is where we stopped last week when we were discussing how the execution actually happens, and we were trying to draw some parallels to MapReduce. So we said that in Spark, just like in MapReduce version 2, there is this resource manager or cluster manager that takes, is in charge of allocating containers and allocating computing resources and so on. And the rest of the system, like MapReduce or Spark in this case, is acting as a client to that. So whenever we want to execute something, we have our driver program. That's typically where the execution begins. That's the code that you write as a Spark user. And the driver program has in it something called the Spark context. And this is the client side of Spark pretty much. So last week we said how, for example, you write your code and that code compiles or defines a graph of operators. Nothing is executed on the cluster until you have an action in your DAG, in your graph. An action is something that requests an output. And the flip side of an action is a transformation. And transformation is something that takes an RTD and produces a new RTD. So nothing happens on the cluster until there is an action. And when there is an action in your graph, then Spark will walk the graph backwards from that action, see which RTDs need to be computed. And then it will need to compute them. It will first try to optimize the plan and then start computing those RTDs. And to compute those RTDs, it will need to go through the resource managers, just like MapReduce. So Spark context will talk to the cluster manager to get containers, so computing resources for its worker nodes. And then on the worker nodes, it will spawn executors. And these executors have a thread pool on which we execute tasks. And then they have also a cache where, well, the data is being cached. And once these executors are up, the context talks directly to the executors to assign tasks and collect the status of running tasks. Okay. We also said how we can have this driver running in two modes, in client mode and in cluster mode. Client mode is what you typically have when you just Spark submit or use PySpark or some other shell-like environment. The driver, so the client side of the application runs, well, on the client side. And what it does is it communicates with the cluster, gets a container, spawns an application master in that container. And this is the equivalent of MapReduce's job tracker. And then this application master will then talk to the resource manager, the cluster manager, to get containers for the executors and so on and so forth. So this is then the mediator. The Spark driver does not talk directly to your executors and the containers. Everything goes through the application master. Okay. The other way of executing programs in Spark is the cluster mode, in which case the client side is just like a thin layer, right? So it's it will you have your code there, but when the execution begins, what happens is that that code is transferred to the cluster side. So you acquire a container to be your application master, and there is where the driver is executed. And there are pros and cons in both cases. The main pro of the client mode, excuse me, the main pro of the client mode is that if you have commands like instructions in your code that print stuff on screen on the terminal, you will see that on the client side because it's the driver that does that. If you run in cluster mode, you won't, because the message would be printed on the console in this container, and you wouldn't see them in the client. That may or may not be a big thing for many. But what you gain by executing the driver on the cluster side is that the driver is now under the control of Yarn. So if it dies, Yarn will restart it. Okay. And I mean, that's one thing. The other thing is that you reduce communication. So you don't have the driver talking to the application master every now and then. Here, everything lives in the same node within the cluster. So there's no communication outside the cluster until the job finishes. Okay, good. So a few things about these executors here. typically we had one set of executors per application, and an application is a Spark program, right? A Spark program might have multiple, the equivalent of multiple MapReduce jobs. Yeah. So you must have seen that in the assessed exercise so far, where you need to do a bunch of things. You need to compute, I don't know, inverse document frequencies and term frequencies and so on and so forth. This would typically be different MapReduce jobs. We could call them jobs in this case too, only they are under the same application. They're started by the same driver. Okay. So we have one set of executors per application, and these executors are, well, the equivalent of Yarn child containers. You have one JVM per executor, but every executor can execute many tasks. You have threads, you have this thread pool in the executor. So multiple tasks can be executed within each executor. Also, we've said that last week, this is one of the main design decisions that made Spark better than MapReduce. You don't need to spawn a JVM, or you don't need a full-blown JVM to just run a map or reduce. You have one JVM, multiple threads in that JVM, and so the overhead of starting a new task is defined by the overhead of transferring the task to the thread. You don't have any spinning up overhead. Practically, there's still a small overhead there, but it's negligible compared to the overhead of spinning up a JVM. These executors can exist even without an active job. So we should try and make this distinction between a job and an application, right? An application is everything that starts from a driver. The driver might start many jobs, but every time a job finishes, its executors do not go away, right? The executors are tied to the application, to the driver. They're not tied to a job. So this is the default, but there is also another mode in Spark called dynamic executor or dynamic resource allocation, which I think is the default these days. Don't quote me on that. I need to double check what the configuration is on our cluster, because that's configured by the administrator. But what happens in this case is that Spark does not. Spark decides on a number of executors at first and spawns that many containers and that many executors. And as processing goes, it tries to monitor how loaded these executors are. So if it sees that these executors are fully loaded most of the time, it will try to spawn more executors. If it sees that these executors or some of these executors are idle, then it will remove some executors and will shift things around. Okay. In any case, in any case, what this means for us is that startup times for tasks are very small now, very low, especially compared to the high startup times of MapReduce. Okay. So before we move on, we have a couple of questions here. Interactive data mining kind of tasks are done usually in client mode. Yes, I mean, okay, it depends on what the interface you're using is. If you're using like PySpark or something similar, then the driver is running in client mode. You could be using something else though, some other front end. And in that case, whether that runs in client mode or cluster mode is to be seen. It's not that, okay, if you run your driver in cluster mode and you need to see the messages on the client side, you need to take care of that. Okay, it's not impossible. It's just that it's not done by default by Spark. You need to put something in the logic of the client that will talk to the driver every now and then to get those messages back. Okay. Will the application fail if the driver fails in the cluster mode? Depends on how it fails. Yeah. If it fails in a way that it can be restarted or resumed, then the application won't fail. If it fails in a way that it cannot be restarted or resumed, then yes, the driver is nothing more than the client side we had in the job in the MapReduce use case, right? It is the case somehow. You might have seen this. I'm not sure whether you've bumped into this case in when executing your stuff against the cluster, or if you've started executing your stuff against the cluster. You could start your driver. The driver submits, gets to the point where there is an action and submits a bunch of tasks to the cluster, and then something happens and you get a disconnect, right? If the driver runs in client mode and you get a disconnect from the cluster, then that job is as good as dead. If you run in cluster mode and you get a disconnect, then the cluster side will continue happily executing, even though you've lost the connection to it from the client side. Okay. Someone asks whether it is feasible to have a map without a reduce. And yes, it is feasible. What is a map doing, right? By the way, do you mean map as in map reduce map, or map as in flat map? Sorry, map as in map the operator, or map as flat map, which was the map reduce map. I'm not sure. In both cases, yes. What a map does is it takes something in the input and translates it to something in the output. And there might be tasks that need just that. Okay. I think we saw an example a couple of weeks ago. So if you wanted to take some, text file, and for every word in that text file, uppercase all the letters or lowercase all the letters, right? So there, for everything in the input, you produce something in the output. You don't need a reduce. You don't need to aggregate anything. And if you don't have an aggregation of any sort, then a map is enough. You don't need a reduce. You haven't seen, okay, someone says, I haven't seen any context creation in Spark programs discussed in lab so far. Context means Spark conf. So to answer that, we need to get into the code. There is some code examples later today. So let's discuss that then. If I forget, please remind me. Okay. There is always a context. There's always a client side. Okay. So let's discuss a bit about execution phases, and then we can get back to what exactly is an RTT. Okay. So we start the execution phase by first instantiating a Spark context. So whether this is done explicitly or implicitly, we'll discuss that later on. Okay, but it does happen. Okay, so the client side needs this Spark context object because that is the bridge to whatever happens on the cluster side. So this Spark context is responsible for I/O with the user. So if you have something like PySpark and you type stuff, whatever you type is communicated to Spark context. But Spark context also talks to the cluster manager and the executors. Okay, so what it needs to do is I'll get to that point in a minute. What it needs to do is also it initialize the driver, and the driver needs to talk to the cluster manager and register the application. That means get an application ID back, request containers for the application master and the executor, and so on. Okay, and then the driver is responsible for the Spark job. Okay, so far it does exactly what the driver did for MapReduce. Okay, now the client will use this context to also create input RTTs. What does it mean to create them? It needs to, it's not creating anything, the data is there. What the context does is it registers records these RDDs. It says that I now have an RDD called something whose data lives in that place, and it has these characteristics. We will see shortly what is in an RDD, as I said. Okay, but it can also decide whether the RDD or how the RDD is partitioned and parallelized across the cluster nodes. Okay, in the default case, you would have as much parallelism as there are splits in that RDD. Okay, how many splits are in the RDD? Well, it depends on the input format. Okay, you must remember the input format from the MapReduce slides, the MapReduce lectures. Okay. The client then would use transformations from the input and intermediate RDDs. So the code you write, creates has these transformations. These sequence transformations creates a DAG of operations, and as we said, nothing is actually executed. No computation takes place so far on the cluster. Everything is in the client and recorded in the Spark context. At some point, there will be an action, something that prints results, that stores results, or something similar, and that's when things will be triggered. Right? So an action will trigger the submission of the DAG to something called the DAG scheduler. The DAG scheduler is still within the driver, right? We haven't gone to the cluster side yet. And the DAG scheduler will look at the DAG and will try to build stages of tasks. We briefly mentioned stages last week. We will see them again this week shortly, right? So these stages, well, they define what will be executed where, and they are pretty much implemented as an event queue. Okay, so you take your DAG, you look at what can be pipelined, where you have pipeline breakers. If you remember this from last week, you group together tasks based on their dependencies and based on whether they can be pipelined or not. You partition them based on how the input RDD is partitioned, because if they can be pipelined, then that partitioning carries on. And then this plan is entered in an event queue. Okay, and what happens is you submit the execution plan to the scheduler as this queue, and you get back responses for everything in the queue. And every time you might not be able to send the whole thing. You might be able to send it a few stages at a time or a few tasks at a time. So that's why you need this queue. Okay. Every time a stage fails, you need to resubmit it if the output was lost. Okay. And then you have this guy, the task scheduler, we just mentioned. And this is still on the client side, where the driver lives. And this is the part that is responsible for sending tasks to executors. Okay. So what this needs to do is it takes the lineage of an RDD. You have this sequence of operations. You say, I want to read this file. Okay, let's focus at one split of the file. I want to read this split of this file. And for everything in this split, I want to apply this map and this filter operation. Okay, all three of these are things that you can pipeline. So for that one split, you have this lineage. You say, read this from that place on SDFS, apply this map, apply this filter, and that gives you an RDD. Okay, so this sequence of operations, you need to serialize them. So you describe them in some form that can be sent over the network, and so you send that to the executors. Which executor do you send it to? This goes back to what we were talking about a couple of weeks ago regarding pushing the computation to the data, not the data to the computation. So you try to send this to an executor that lives on the same machine as where the input for that RDD, for that sequence of operation lives. So everything happens locally, you don't have network transfers. If you can't do it, then you try to send it to an executor that is on a machine on the same rack. If you can't do it, then any other machine would be okay. Okay. And then the task scheduler monitors the execution of this computation and the progress. So it will launch tasks on the executors, and it will, as I said, decide where to run each task. And it will also deal with stragglers. So in MapReduce, we had this thing that was the speculative execution mechanism. So every time we had a map or a reduce that would take much longer than others, the system cannot know whether that's happening because the task itself is too complicated, or whether something is wrong with the machine where this task is running. Okay, so it will speculate. That's why it's called speculative execution. It will speculate that something's wrong with the machine, but we don't know what. Maybe the machine is overloaded. Maybe something else. We don't want to stop that guy executing, but what we will do instead is we will find some other nodes in my cluster, and we'll have them execute the same task at the same time. And whoever finishes first is the winner. We take that guy's output, and all others can be terminated. So that mechanism also exists in Spark. And I hope you're seeing this pattern. Spark is just MapReduce with some added sauce, right? So some very interesting design decisions to make aspects of the MapReduce logic faster. And then other than that, most of the changes are in the surface, okay? So the task scheduler, will monitor this execution, and every time there is a result to be returned, it will return this result to the task scheduler, okay? And this is again done as a series of events, because the task scheduler needs to, for every event that it gave, for every event the DAG scheduler gave to the task scheduler, it expects to see a response, okay? You can think of this as the equivalent of callbacks or continuations in async programming, right? Because this is exactly what it is. Okay, let me see if there are any questions before we go on to RTT. Okay, someone says that we cannot test or view the driver fail scenario in lab because everything is running in a single system and all programs in a single JVM. That is the case when you write the code and run everything on your local machine. If I'm not mistaken, the plan was that at some point you would be executing your code on a cluster. And in that case, if you haven't done this already, you will eventually. And so when that time comes, you might actually see this driver fail scenario. Okay. Right. So let's see what this RDD is all about, this lineage. The RDD lineage records these things. First of all, input partitions. It records, actually, let me just uncover all of this. Okay. It records what the splits are, and these are equivalent or similar to Hadoop MapReduce's input partitions. So what do we need to know for every partition? We need to know where it lives, where it begins, where it ends, right? If we're talking about an RDD built on a HDFS file, then the source is the HDFS file name, or the HDFS, I just say file name. And then the split is, which block and which offset in the block is the beginning of the split, and which block and which offset in the block is the end of the split, right? We also need to record dependencies on parent RDDs. So we say that we have an RDD, it has a split, and this split depends on such and such splits of its previous RDDs, okay, its parent RDDs. If we read stuff directly from HDFS, we don't necessarily have dependencies because there is no parent RDD. But if we have, let's say, we have an RDD created by reading stuff of HDFS, and then we apply a map to that, for the map RDD, or the RDD that is the output of the map transformation, we need to record what are the splits, and then for every split, what split in the parent it was created on, okay, or created by. We also record the function. So what transformation or whatever was used to compute the current RDD given its dependencies. Okay, this is the code you write, pretty much. So this can be a map, it can be a filter, it can be pretty much anything. Okay. There are two more optional things that you can define here. One is preferred locations. And you can use this to enforce data locality. You can actually tell an RDD that I want you to have locality of X. Okay, I want you to always be executed on the same node where the data lives, or things like that. This is optional. Okay, you may or may not do it, and it may or may not be able to be enforced. But there's also a partitioner preference. So, and this is pretty much like defining your own partitioner in MapReduce. So you may or may not want to do it. And if you want to do it, then you have the built-in partitioners are a hash partitioner and a range partitioner. But you can write your own partitioner if you want. And what it does, it tweaks the shuffle phase, just like MapReduce partitioner. Okay. So let's say an example. Let's say we read data of an HDFS file, and that creates an RDD. So in this case, the partitions are the HDFS blocks, one partition for every block, because let's say that is the input format we're using. The locations are the HDFS block locations. Okay. The compute function is just read the block. And there are no dependencies and no partitioner in this case. Okay. Let's say we have another RDD that is created by filtering something else. Okay, we have an RDD and we apply RDD.filter to that and we get the output. So in that case, the partitions of the output RDD are the same as the parent RDD partitions. This means that for every partition in the parent, we have a partition in the child. And this dependency is one-to-one, actually. Okay. So we have as many partitions as there are partitions in the parent, and every partition in the child corresponds to one partition in the parent. The function that we apply to the parent partition to produce the child partition is, do whatever you need to do to produce the parent, and then apply the filter operation on it. The location is the same as the parent, and there is no partitioner here. Why is the location the same as the parent? Because this is one of those operations that can be pipelined. Since for every partition of the parent, you create one partition of the child, it makes sense to execute this or to assign a partition of this RDD to the same place where its parent partition lives in the cluster. Okay. Is this clear? So did this answer the questions about RDDs? Okay, I got a yes there. I hope it's the same. It comes from the same person who asked these questions, because slide is anonymous, so I can't really tell. Split dependencies or RDD dependencies, they are actually the same. So every child RDD depends on one or more parent RDDs. But what does this mean? It means that every partition of the child RDD needs data from one or more partitions of one or more parent RDDs. So the dependencies may be defined at the RDD level, but utterly they translate at the split level, because that's what we need to do to compute the output RDD. Can I explain again the dependency? There is, I guess, an example coming on. I think it's the next slide or slide after that. Okay. Other than what we see here, the other thing that you need to remember about RDDs is that they are immutable, right? So if I have an RDD, I can never change the data within that RDD. I conceptually create a new RDD that has the changes I wanted to apply to the existing RDD. Yeah. So let's move on, and we'll see. We'll try to address the rest of the questions. So there's a bunch of operations already built in. Okay. I'm sure you have seen this again in the lab, and probably you've seen more than this because it's just a small list. I'm sure there is at least one transformation that is not in this list. So I mean, what do I want to take away from this slide? Because again, I think you've seen all of this in the lab. You have your transformations, and every transformation takes some RDD or more than one or more RDDs and produces an RDD in the output. And actions take RDDs and either produce a value in the output, a value that can be, let's say, printed on screen or whatever, or they store stuff on disk. So there is some kind of output. Okay. I mean, we can go through these and explain what they do. I'm not sure that would be of value. Or actually, let me just do it very quickly. Map takes an RDD, and for every item in the source RDD, creates an item in the output RDD. Okay, 1 to 1. Filter will take an RDD in the input. For every item in the input, it will apply a Boolean function, a function that returns a Boolean. If that function returns true, then whatever that item is in the input, it's copied to the output. If the function returns false, then that item is dropped. It's not copied to the output. Flat map is actually, by the way, flat map is the equivalent of map reduces map. So for flat map, we take an RDD of items, and for every item in this RDD, we apply a function that may produce 0, 1, or more items in the output that may or may not be the same as the items in the input. Okay. So this here is the equivalent of MapReduce map, because you may remember how in MapReduce, for every item in the input, we can have 0, 1, or more items in the output. Okay. Whereas this map here at the top is an 1-to-1 function. There is a sample transformation, and this is a deterministic sampling. So for every, I mean, exactly, if you want to know the, I'll get that. So if you want to compute an X% sample, I think last time I checked that how this is computed, this is implemented. What happens is that you go through an RDD and you pick out the first that many items, and there was some way to maybe affect that. But this is, you get an RDD with some items, you pick out some of those items and you copy them to the output, and that's a sampling. Okay. Group by key and reduce by key. Both of these can be thought as being the equivalent of map reduce reduce, or combiner to some extent. There is no, I have these stars up here because you might see these mappings online too, if you look around, but this is not exactly correct because you don't really have a way in Spark to tell it to run this reduction on the left side of the of the flow. So how in map we had the mapper. The mapper did stuff, produced something in the output, and then we applied the combiner there before we pass it over to the reducer. Okay, there is no clear way to do that in Spark. Okay. Union. Oh, by the way, I mean, what group by key does is it takes a bunch of an RDD that has a bunch of keys and values and groups them by key. So it produces an RDD that has key values where the key is a distinct key and the value is a sequence of all the values for that key. Okay. Reduce by key takes an RDD that has keys and values, like a sequence of keys and values. And what it does is it groups together all the stuff that have the same key, and then applies a reduction function, a function that takes two values and returns one, and applies that iteratively or recursively, depending on how you want to look at it. You can think of this reduced by key as, this is not what happens, but you can think of it as running a group by key and taking this RDD where you have a key and a sequence of values, and then going through the sequence of values and combining them, the first and the second, and the result of that with the third, and the result of that with the fourth, and the result of that with the fifth, and so on, until in the end you have a single value out of all of these. Okay. The union takes two RDDs and produces an RDD that has the data from both RDDs. And we will see later on that this is actually one of those operators that can be pipelined, because what happens is that for every split, every partition of an input RDD, you just copy that partition to the output RDD. So this output RDD is just the union of the partitions of the source RDDs. Okay. A join does pretty much what it says. So it expects two RDDs. These RDDs are sequences of keys and values. And what it will do is it will produce all possible combinations of keys and values from these two RDDs where the key is the same. So it's computing an inner join pretty much. Okay. Call group is sort of a smarter way of doing the join. The logic is the same, only that you don't produce one key and combination of value pairs for every combination of every match of key value pairs in the input RDDs. What you do is you can think of this call group as the equivalent of executing a group by key on the left RDD, a group by key on the right RDD, and then a join on the outcomes of these two. Okay. Yes, cross product, what it says on the box, right? So this is just the Cartesian product. Map values, this is like map, only here you assume you have key value pairs in the input RDD. And what you do is you apply the map function only to the value. So you get a bunch of key values here. And for each one of these key values, you apply a map function to just the value. You produce a key value pair in the output with the same key and the output of that function as the value. Okay. Sort, well, again, it does what it says on the box. It takes an RDD that consists of keys and values, and it will sort it by key. Okay. And partition by, this is your way of repartitioning RDD. So you can take an RDD consisting of a sequence of keys and values, and then you have a function on the key that tells you what partition it will be assigned on in the output. So you can take an RDD that's partitioned in any way and repartition it in any way you want. Okay. Someone asks what's the difference between reduce and reduce by key. I'll get to that in a minute. Okay. These are all transformations. There is also an aggregate by key, which is missing here. Aggregate by key is quite close to reduce by key in logic. But then we have these actions, right? And you see what these actions do. We have a count action that will take an RDD and it will return a single number, this single number being how many items are there in this RDD. We have a collect function. This is actually very popular. People tend to use it all the time. And it's one of the main reasons why your code might crash. What collect does is it takes all the items you have in your RDD, transfer them over to the driver side, and materialize them in the driver's memory. Okay, so it goes from a distributed sequence or a bag of items to a bag of items on the driver side. Okay, I mean, this can be useful if, for example, you have computed something on the cluster side and then you want to print it on the driver side. But people often in the past were using this collect action without actually thinking what it does. Okay, collect would get everything out of the cluster to the driver. All right. So if you're doing stuff in your code where you compute, and then you collect, and then you take whatever you collect and you continue to compute, keep in mind that what that does is it computes stuff on the cluster, takes everything out of the cluster into your driver memory, takes everything from your driver memory back to the cluster, continue the computation. Okay, be very careful with collect. Right. And then we have, I'll leave reduce for last. Lookup, I mean, what it does is it takes an RDD that is supposed to be consisting of keys and values, and it has a function on that accepts a key, and what it will do, it will return all the values of all of those pairs where the key matches whatever was passed to it. Okay, but this is returned again to the driver side. Okay, it's not on the cluster side. If you wanted to do this on the cluster side, you would probably use filter. Okay, lookup will get stuff out to the driver, and save will store whatever is in the RDD to a storage system, HDFS by default, or if you're running in local mode, it could be a file on your local file system. If you're running on I don't know, on some cloud, it would be some storage on the cloud, whatever. Okay. Reduce, let's this for last, it takes an RDD and it reduces it down to a single value. Okay, out of all the RDD, you get a single value. Compare this to reduce by key, where for every key, for every distinct key, you get a value. Okay. Someone asks, what do I mean by collect? Is this collect the Java like stream collectors collect, or is it a Spark specific thing? This is a Spark specific thing. Okay. This is an action in Spark. Okay, it's not the same as the stream collectors or the, what they call them, collections, collect. This is a different thing. Okay. There are a few questions about like information on Java or Python or examples of code. I would suggest that, I mean, I'm not sure whether Richard is here now, but this should be better discussed in the lab. Okay. I mean, I'm happy to propose sources, but I'm sure Richard has his plan on how to share and where and when. So if you think you need more information, more resources, please do talk to Richard and or the lab assistants, of course. Okay, this took way longer than I wanted to take. So let's discuss a little bit about, or was there any answer, any question I didn't answer? Oh, right. One thing here. Someone says transformations are logical tasks, but actions are physical, actual tasks. So transformations only logically manage the task using lineage. I think I will agree with what you say. I mean, this is getting a bit philosophical, but yes, to some extent, transformations are you don't. So transformations will produce nothing you want to see. What you want to see is the output of actions. Okay, when you evaluate the transformations, there are physical tasks being executed. So I'm not sure about transformations being logical versus actions being physical. The key difference between the two is whether there is something as an output. So all of these things here, for the first 4 actions, these are things printed on the screen or returned to the driver. Yeah. For this last one here, this is stuff written on this. So there is some output being produced. That's the main difference. Okay, so let's talk a bit about stages again, and then we'll take a quick break. Stages are created based on RDD dependencies. So what we need, how we can think about this, right? So if I have a child RDD, and I focus on just one partition of the child RDD, right? Let's say that's partition X. What do I need to compute the data that would go into that partition? Okay. And the corollary of that is, if a parent partition dies, then what do I need to do to recompute what I need to compute in order to get my partition X data? Okay. And in Spark, in Spark lingo, we have 2 types of dependencies: narrow dependencies and wide dependencies. Narrow dependencies is when every partition of a parent RDD feeds or is used by at most one partition of the child RDD. Okay, so think of map or filter or union. Okay, so if you have a map for every partition of the parent RDD, we said earlier, you go through this partition, you apply the map function to every item in here, and for every item you produce an item in the output. So this partition here will feed one partition of the child RDD. Okay, same with filter. With union, we said that what happens is we just copy the input RDD splits to the output. So every split in the output is fed by one split in the input, and every split in the input only feeds one split in the output. A special case of this is joins, where the inputs have been co-partitioned. So if you have a, let's say this is a table and this is another table, okay? And we have partitioned these tables such that this first partition contains only keys A, B, C, and this first partition contains only keys A, B, C. And then we have DEF and DEF and GHI and GHI and so on. So then when we want to create a partition of the output of this join, we need to get only this partition and that partition, like those partitions that have the same set of keys to be joined. Okay, so this is again a narrow dependency, because every partition at the parent feeds only one partition at the end, at the child. Okay. Now, whenever we have a narrow partition, this is something that we can pipeline. And by pipelining, I mean this task can be executed locally at the location of the parent RDD. So if I have, let's say that this is an RDD created out of an HDFS file. Okay. Again, keep in your mind that what does this mean? It means that in my code, I have a RDD whatever equals Spark context dot read from file, whatever. Okay, nothing has been executed yet. I've just defined that I have an RDD whose input, whose splits map to splits of a file on HDFS, and the data that I need to compute is whatever data is on HDFS, and the function to be applied is just read the data from HDFS, and so on and so forth, right? So I said I have a partition here, but I don't actually have the data in main memory yet. Data is still on HDFS or wherever this partition is fed from. And then I say I want to apply a map on that partition, okay? And I know that the map is an arrow dependency. So for everything for every split in the input RDD, I will create one split in the output RDD, okay? Or at most one, right? So what this means is I can sort of collapse this together. So if I was a programmer, I would write a single function that would read the data from HDFS and apply the map. Okay. And this is exactly what you would do if you were writing MapReduce code. So what happens here is that Spark is trying to take some of that, let's say, dark art of combining things together in MapReduce away from the programmer. Okay. All right. So whatever is the function applied here, like map, this map would be applied on that RDD. That RDD would be created somewhere, and both of these would be executed on the same node. Okay, for a split of the child RDD. For this split of the child RDD, the second one, I need to read that split of the parent RDD. For that parent RDD, I need to read data from some place on HDFS. So this would be scheduled somewhere to be close to the data, and then that somewhere is where the map function would be executed to. Okay. Why dependencies on the other side are dependencies we have when multiple child RDD partitions depend on one parent RDD partition. Or to put it the other way, where one parent RDD partition feeds more than one child RDD partitions. Okay. Group by key or joins or reduce by key, these are all wide dependencies. Okay. So another way to think about this is, do I need to shuffle? Whenever I shuffle, I have a wide dependency. Okay. And last week, we actually draw a parallel, which is exactly how this was designed. These are operators that can be pipelined, and these are pipeline breakers. Okay, this is how we would call them in a traditional database lingo. So wide dependencies are exactly pipeline breakers. And what happens then is that data needs to be shuffled. And how do we shuffle the data? Well, pretty much the same way we do in MapReduce. We need to store the data, maybe in main memory if it's not big enough, but typically on disk. And subsequently, that data is accessed over the network, just like we would do with MapReduce shuffle. Okay. There is a special case that is, unless the parent is hash partition, and this is pretty much like this case here. Okay. Now, data can be repartitioned. You can have, I mean, there is a repartition transformation that is also a wide dependency. And you can repartition your data at will. Sometimes it pays off to repartition before applying a narrow or a wide dependency. Why is that the case? Typically, repartitioning is not a too expensive operation. Okay, depending on whether you go to more or less partitions, what you do pretty much is you either like split or combine your splits. Okay, but what you get after the repartitioning is a different definition of how parallel I can go, because as we will see shortly, when you go through these dependencies and you create your stages and you create your pipelines of tasks, how many pipelines you have defines what is the maximum number of tasks you can have running in parallel. Okay, so you may want to reduce the number of like the level of parallelism. For example, if your cluster is low on resources or for whatever other reason, or you may want to increase the level of parallelism if you have too strong of a cluster and you have a very small file and you're not taking advantage of all of the parallelism, for example. Okay. And let's actually, yes, let's take a quick break. I'll stay on this slide. There's a question about what happens during shuffling. We'll address that later on. Let's take a quick break, 5 minutes. So it's 12:04. Let's go to 12:09 sharp. And we continue then. Okay, 5 minutes. Okay, good, let's continue. So as said earlier, someone asked what happens during sampling. That is a long discussion, because when Spark first came out, it did one thing, and then that thing was not efficient enough, and then they did a different thing. Okay. There is actually a question, I believe, coming later on today. So I'll save that question for later too. There was one more question that we said we will save for later. Please remind me if I forget by the end of the lecture. Okay. So, okay. So what happens is, let me see. Oh, yes. How many quizzes are left? There are 2 more quizzes left. We will have one next week when we go over the first batch of SQL, so Bigtable, HBase, and we'll have one more either the week after that or in 2 weeks' time when we go over. Next week we will be discussing distributed NoSQL cloud stores. After that, we will be discussing decentralized cloud stores. So there will be one quiz for each one of these. Okay, and no more quizzes after that. Okay. Sorry, I think I saw that question earlier and then completely forgot to address it. Okay, so back to this then. So again, what we do in our code is we write the code, we define the RDTs, we define their dependencies and so on. You know what the transformations are, and at some point there is an action. And when the action comes, we said that Spark will try to optimize the plan for us. What does that mean? Okay. First of all, it will look at all the dependencies. Whenever it finds narrow dependencies, it pipelines those operations. So it packs them together so that whenever it sends whatever executor is assigned to execute the code for the very first operation in the pipeline will also be the same executor that will execute the code for all the subsequent operations in the pipeline. Okay. And that defines a stage. You remember how we said, I think last week, there is an image coming on, that whenever we have a bunch of operations that are narrow pipelines and can be pipeline or narrow dependencies, and then we find a pipeline breaker, a wide dependency, then that defines the boundary of a stage. And everything in a stage can be executed concurrently. So we can, we smash those pipelines, and that gives us a bunch of things to do for every partition, for every split of the input RTD, and those can be executed in parallel. Same thing if we have other stages that do not depend on anything this stage is computing. That can be also executed in parallel. Again, we smash everything that can be pipelined, and we assign those things to wherever the input partition lives. Okay. So we group and pipeline narrow ops in a stage, and then we choose the task placement and the shuffle algorithm to minimize data transfers based on partitioning. Okay. What does that mean? We are always trying, remember, to push the computation to the data. Sometimes the data comes from HDFS or from disk, so we're pushing the computation where that thing lives. There are other times where the data is not on a disk, but it has been computed and cached in memory as a result of a previous computation. So then that is where the data lives, in memory on some nodes. So in that case, we are pushing that computation there. Okay. Right. So whenever we need to do that, we need to check where data has been cached, and or what are preferred locations defined in the RTD. any intermediate results that need to be materialized, they will be materialized wherever the parent partition lives. Okay, if that sounds familiar, that is because that's exactly what MapReduce was doing with the intermediate results of the map function. Okay, and we are trying to reuse previously cached data as much as we can. Okay. Just a minute. I think someone is at my door. I'll be right back. Apologies. So that's the first part of the optimization, right? Trying to push as much computation as we can to the data, trying to have to recompute as little as we can, reusing previously cached data as much as we can. And you must have seen it in the labs that when you execute something in Spark, the data is not cached by default. Okay, there is a called an operation. It's not a transformation. It's just something you add to your DAG. You know, you can say this rtd.cache. Okay, and that will try to cache the RTD in memory. You can also try and set its what's the term? Its durability level. Might be mistaken on the exact term. So you can define that you want it to be cached in RAM or in RAM and disk or on disk and so on. Okay. So what that will do is it will store, or it will try to keep that RTD, the data in the RTD, right? The data that is the result of applying all of the transformations to produce that RTD in memory or on disk to be reused. So this is an example we had seen last week too. So now that we have a somewhat better understanding of this, let's try to go through it. Okay. So let's suppose that these things that are at the very left side of this job, they read stuff off of SDFS, let's say. Okay. So A is an RDD that is created by reading data off of some file of SDFS. And C is an RTD that's created by reading data from some file on XDFS. Okay. So here we are supposed to be doing a read and then a group by, let's say, group by key. Okay. Now a group by key is a wide dependency. So this means that this is a pipeline breaker. We need to terminate this first stage here. So we have a stage that is just reading stuff of HDFS. Then here we read stuff and then we apply a map and the filter. The map is a narrow dependency, and so is the filter. So all of this can be pipelined. There's no reason to break the stage here, but here in the end we have a join. Okay, and the join is indeed the wide dependency. So this is a pipeline breaker. We draw the boundary of this stage here. So now we have these two stages. Okay. This is something I would expect people to ask me. Why are these lines straight? I'm doing a join. Why are these lines like intermixed like this? Why do I have a full shuffle here and I don't have a shuffle here? Anyone can guess? Those are sorted almost. because of the group by exactly. So it's not that B and F are already in the stage, it's that the group by has already created partitions where things are grouped by key. Okay. Whereas here, map and filter has done nothing with the keys. So if I want to produce this output here, this block of the output, I might need data from one block of this input, but I might need data from multiple blocks from this side. Okay. So that's why only this side is a shuffle, not this side is a shuffle. And actually, looking at this, where do you think the join would be computed? Like which side would we prefer in this case? If everything is as we see here, I mean, if the output is just 3 partitions, where do you think these partitions would be executed? These partitions would be computed. Sorry. So B side or E side? That's the question. Okay. So a few people say at B, there's one at E. I leave this as an exercise to you, but I think what we've said so far should give you enough to decide. So remember, we're trying to pipeline things as much as we can. We're trying to reduce the data we transfer around the network as much as we can. Okay. So is it better to do the shuffle to the B side, or is it better to send this to everything here on the A side and then produce the output? Think about it. Okay. Now, what I was alluding to earlier was that what is a task here and what is the parallelism? Okay. So this partition and this partition and this partition, or the splits of the A RTD, they can be computed in parallel. Okay, I can have these 3 tasks running in parallel. I can also have this task here. Now, what is a task here? Reading this partition, applying the map function, applying the union function. This now is a task. So this task can be computed in parallel to this task, which is computed in parallel to this task and in parallel to this task. Okay. So I could have all of this running in parallel, and whenever I have the end of the stage or the end of the, or where I have this pipeline breaker, I need to wait for all of these to be completed before I can continue on with the next stage. Okay. All right, so far. If we were writing MapReduce code, then we would need to do this on our own. So we would need to think that, wait a minute, I'm reading stuff off of HDFS. I'm applying a map that, I mean, by default happens in one function in HDFS. That's just the map function. But then I have this union. There's no reason why I cannot just copy this to the output. I don't even need a reducer to do this. Okay. That's a good question. So someone asks, are all tasks within a stage executed strictly within the same executor? Every task, so if this horizontal thing here, like first partition of C to first partition of D to first partition of F, this is a task. This task will be executed at a single executor, but this task below it will most probably be executed at a different executor. That different executor being defined by where this input data is. Okay. People are still trying to answer the question of where is the computation happening, B or sorry, here, B or E. It's not that simple. right? So if you want to transfer B to E, you need to transfer every part of B to every part of E. Yeah, maybe the same way, the other way. Think about it. Think about what is the total computation required to compute the join, which is a filtered Cartesian product. Anyway, are there any more questions on how stages are created? So here, someone asks, why do we have 4 partitions at F here? We have four partitions because union, as I said earlier, does just that, a union of the input partitions. Okay, so if I had 10 partitions here and 20 here, I would have 30 partitions in the output. And this is so that this is a narrow dependency. There is no reason why it shouldn't be a narrow dependency. Okay. All right. Cool. If there are any more questions about this, feel free to ask them. I'll go ahead, and if there are any more, I can come back and answer them later. Okay. So we've been talking about data locality for some time now. The basic idea here is the same as in Hadoop MapReduce. We try to avoid network I/O as much as we can. And so what that means is we try to transfer the processing to the data. Or, to put it in different terms, we want to work only on local data if that is possible. Okay. But Spark does something that Hadoop MapReduce didn't do. It does caching. So how does this work? The first time a file is accessed, it's read off of HDFS, or whatever the source is. And we can cache it. Okay, we can say read this dot cache. Okay. Locality here is controlled by HDFS or whatever the source is. So we will try to assign this transformation, this creation of this first RDD, to an executor that runs on the same machine where the input partition is stored. If we have HDFS and we have partitioned and replicated data, we could pick any of those replicas for any of the blocks. And what would happen in actuality is that the task scheduler we mentioned earlier would look at where these blocks live and would try to devise a way of assigning tasks to executors so that all executors have the same amount of work, more or less, and all of these transformations, these original transformations, happen locally. Subsequent accesses can use the cache. Okay, so if I have cached my data, if I have cached the output of that RTD, then the locality is controlled by the cache. Okay, there is a side note here, and that is that there is a mode of caching that says keep this data in memory, and if it won't fit in memory, throw some of it out on disk, right? So that is what we call caching out. So if the data is cached out, that would happen, for example, if the executor runs out of memory or out of cache memory. Okay, and why would that happen? Well, remember, every executor is executing tasks from possibly multiple jobs, possibly or typically multiple tasks at the same time. And all of those tasks might be requesting that their output is cached, right? But the executor only has a finite amount of memory available for caching. So it might run out of memory, right? In that case, data will be cached out. So if data is not in memory somewhere, if I want to apply a transformation on some partition, and the task scheduler sees that that partition is not cached anywhere, then it will fall back to HDFS locality. Okay. Shuffling. So this is one of the questions I said I would cover later. So that box is being ticked now. Shuffling in Spark happens much like in Hadoop MapReduce. So whenever I have, I'm finding myself in that pipeline breaker situation. The output of the transformation I have on the left is partitioned and stored on the local file system. Okay, and data is serialized on writing and deserialized on reading. We discussed serialization in the past. If you don't remember what this is, let me know. Okay. Now, when Spark first came out, there is this question here: how many shuffle files for mmap and R reduced tasks? Okay. When Spark first came out, it had this very simple logic that said every task on the left will create an output file. Okay. And that output file, sorry, every task on the left will create one output file for every task on the right. Okay. So if I had a map reduce situation and the shuffle in the middle, I would have m times r files created on the map side. Okay. M times r shuffle files. What they saw though going on was that was very inefficient. First, that would lead to a large number of files being created. Every file has its own overhead, and you sort of alleviate that overhead if you have all of them combined. And there were other reasons why this was inefficient. So what they did was that actually in I guess the last lecture of the semester, we will see a paper that came out of this work, or a paper that sparked this work, no pun intended. So there were these guys who said, okay, Spark is good and excellent and super fast and whatever. How do we know? We know because the Spark